My name is AJ Both, and I'm an Extension Specialist in Control Environment Engineering at Rutgers University. In this overview, we will take a look at improving the energy efficiency in commercial greenhouses. Over the years, the industry has come a long way from using simple heating systems like the smudge pot to high-efficiency hydronic boilers that deliver heat to multiple greenhouse zones. The commercial greenhouse industry in North America is highly diverse and as a result uses a large array of techniques and technologies to grow crops. It is not possible to discuss all the different energy systems used across the industry in a short presentation. Therefore, a few selected topics will be presented. These topics include glazing materials, energy and shade curtains, root zone heating, high-efficiency heaters and condensing boilers, energy storage, LED lighting systems, variable frequency drives for pumps and motors, and computer control. The invention of the air-inflated double-layer polyethylene film covering system in the 1960s has had a major impact on the greenhouse industry. A small fan continuously blows outside air between two layers of plastic greenhouse film. This layer of air stabilizes the covering system and increases the insulating value of the structure. Polyethylene films do have to be replaced every 3 to 4 years, but this relatively inexpensive covering system typically results in short payback periods. Shown is the very first greenhouse covered with two air-inflated layers of plastic film at Rutgers University. The greenhouse was dedicated as a historic landmark in 2004 by the American Society of Agricultural and Biological Engineers. Twin-walled rigid plastic panels are another energy-saving greenhouse covering system that is widely used across the industry. The air trapped within the glazing material reduces the heat transmission from the inside to the outside of the greenhouse. Most plastics deteriorate over time as a result of the UV radiation that is part of sunlight, and the picture in this slide shows the difference in light transmission between newly installed acrylic panels on the left and old, more than 15 years old, polycarbonate panels on the right. Rigid plastic panels last longer than plastic films, but they do need to be replaced from time to time. For single-pane, glass-covered greenhouses, it is tempting to install opaque insulation board on the north-facing sidewalls during the wintertime. However, during the wintertime, there is still some amount of diffuse light entering the greenhouse through the north-facing sidewall. In order to add insulation, but still allow some of that diffuse sunlight to enter the greenhouse, this innovative grower installed bubble wrap on the inside of the north-facing sidewall. Curtains installed in greenhouses typically serve two purposes. During the day and in the summertime, they are used to reduce the amount of sunlight reaching the crop. And at night and during the wintertime, they are used to reduce the heat loss from the growing area. Typically, the same curtain is used for these two purposes in order to limit the installation costs. However, installing multiple curtain systems would allow each curtain to be fully optimized for its intended use. In this picture, the curtain is used to reduce the amount of sunlight reaching the crop so as to avoid plant stress. Note that distinct shadow patterns are visible, indicating non-uniform lighting conditions across the growing area. This picture, taken at the end of the day, shows the curtain being closed so that the heat delivered to the growing area is better contained during the night. Reductions of up to 30% in energy consumptions throughout the heating season have been reported when growers use energy curtains to reduce heat losses. Greenhouses can lose heat from air movement through unintended cracks and openings. We call these losses infiltration losses. Greenhouse fans are typically outfitted with louvers on the inside of the fan housing, as you can see in the insert. This placement limits the impact of the louvers on airflow. However, these louvers tend to seal the opening less precise as they have been in operation for some time. The resulting openings can greatly increase infiltration losses. In order to provide a much better seal between the greenhouse environment and the outdoors, when the fans are not in use, this grower installed so-called roll-up vent louvers. Root zone heating systems deliver heat energy to the immediate vicinity of the crop. This reduces heat losses and in some cases allows growers to maintain lower air temperatures, resulting in further reductions in heating demand. Many crops respond very favorably to root zone heating, and the heat is typically delivered very uniformly. This slide shows a benchtop heating system that is installed directly below the seedling flats. A plumbing system with valves and a pump enable the recirculation of warm water to the delivery tubes and back to the water heater, which is not visible in this picture. The floor heating system shown in this slide consists of heating tubes embedded in the top layer of the floor. In this case, the floor consists of soil covered with a landscape fabric and concrete walkways. While root zone heating systems are efficient, only moderately warm water temperatures can be used so as not to damage the plant roots. As a result, additional heating capacity in the form of perimeter and overhead heating pipes are needed to make sure that the greenhouse can be maintained at the set point temperature. High efficiency unit heaters can reduce the consumption of heating fuel. These high efficiencies are possible by recovering most of the heat contained in the exhaust gases as water vapor. In order to ensure that the air used for the combustion process does not contaminate the greenhouse environment, it is kept separate from the air inside the greenhouse. Note the two PVC pipes that deliver and remove air to and from the unit heater. Condensing boilers save energy by recovering heat energy from the water vapor that was produced during the fuel combustion process. Condensing the produced water vapor recovers heat that can be used to preheat water returning to the boiler. The conversion efficiency of condensing boilers is very high, often easily offsetting any increase in purchase price over just a few years of operation. It can be beneficial to store warm water as part of the greenhouse heating system. Having this capability can increase overall system efficiency because the boilers can operate at optimum efficiency for longer periods of time. These systems can also deliver instantaneous heat energy when it is needed. LED lamps are generally more efficient in converting electricity into light suitable for crop production compared to high-pressure sodium lamps. In addition, other benefits such as less heat production and options to adjust the spectral composition of the light make LED lamps an attractive alternative. More information on LED lamps for crop production is provided in another presentation in this series. It is common for fans and pumps to be either on or off. Some fans or pumps have a few intermediate settings, for example, allowing them to operate at half or full speed. However, it is likely that even with multiple operating settings, the fan or pump is working harder than necessary at least some of the time, and this wastes energy. Variable frequency drives, or VFDs, are systems that allow an electric motor to be operated at a continuously variable speed. Thus, their speed can be exactly matched with the demand in terms of fan or pump capacity. VFDs increase installation costs, but greatly increase the energy efficiency of fans and pumps. Computer control can save energy by making frequent adjustments to maintain the desired growing environment, while reducing the energy consumption associated with maintaining that environment. In the schematic shown in this slide, a temperature increase during a sunny day is observed by a sensor that relays that information to the computer control algorithm. Since the algorithm detects that the current temperature is above the set point temperature, it sends a signal to turn on the ventilation fans. As soon as the greenhouse temperature drops to the desired set point, the computer algorithm will turn the fans off. This process repeats itself many times a day and can incorporate additional information such as plant and weather status to make sure the plants get the best growing environment at the lowest possible cost. Note that the computer control system also archives sensor data and control decisions, making it a powerful resource for troubleshooting and for comparisons using archived data. Computer control systems require additional hardware to operate properly. That hardware includes sensors, power supplies, wiring, and electrical relays or switches. All this requires careful installation and periodic maintenance. Sensor calibration is an important tool that helps ensure the control system is operated as intended. Growers are encouraged to follow sensor calibration procedures at the proper time intervals. Neglecting to perform timely calibrations can negatively impact any anticipated energy savings. In summary, a variety of different energy saving strategies are available for commercial greenhouses. This slide identifies the most common strategies that growers use and the typical energy savings that can be attained. Note that the percentages listed are not additive, meaning that implementing multiple energy saving measures will result in less overall savings than the sum of the percentages listed on this slide.